Hi, I'm Fernando Pereira from UFMG, and today I shall tell you about a few compiler optimizations that are enabled by divergence analysis. I chose to talk about 4 optimizations, however, there exist many more. If you want to know more of them, I'm listing some papers at the end of this class. The first optimization is simply removing synchronization barriers at the end of uniform branches. I call uniform a branch that is controlled by a uniform predicate. This optimization is described in NVIDIA's program manual. I've copied the important part here. But something much cooler is register allocation. Do you remember register allocation, don't you? And one question, where do you spill variables in a GPU? Each thread that runs in a warp must have a location for spills, right? So we can try to join these locations for uniform variables. Let's see how that works. Just as an example, let's use linear scan to demonstrate how to improve register allocation using divergence analysis. The actual allocator is immaterial. We could do graph coloring, anything. Any algorithm would do. We care only about where variables are spilled. So in linear scan, if you remember, we color the intervals that represent the live range of variables. In this example program, we have uniform live ranges in orange here, and we have divergent live ranges. I've colored them in blue. A GPU has different kinds of memory. There is one type of memory that's called local. That means that each thread sees its own local memory bank. Usually, threads map spilled variables there, but this is not a good idea because the local memory is off-chip and it's very slow. One thing that the compiler can do is to map uniform variables to another kind of memory called shared memory. The shared memory is much faster because it's in-chip, not off-chip, like the local memory. And because the variable is uniform, we only need one copy of it per warp. That really saves space and speeds up programs. Another optimization that we can do is to reorder threads to avoid divergences. For instance, do you remember that kernel that decrements the positions of an array? How could we change the input array to mitigate divergences? Well, in principle, if we sort the array, then we reduce divergences, because threads in the same warp will perform similar amounts of work. However, sorting the whole array can be very slow. Instead of sorting it, we can try to quasi-sort it. That means reducing a bit the entropy in the array, trying to place similar data closer. We can perform this quasi-sorting in parallel, in constant time. I'm giving an algorithm here for an SIMD machine. First, we read the content of the array to share memory. That's step 1, right here. It's faster to work on shared memory than to work on the array in global memory, because shared memory is within the GPU chip. In the last step, down here, we copy the quasi-sorted array back to global memory. So let's then look at steps 2 and 3 to see what they do. In step 2, we partition the array among the threads, and each thread uses a sorting network to sort the data that it receives. A sorting network is a sequence of operations that always sorts its input data once it runs, so all the threads execute the same operations. So as an example, imagine that we have 4 threads, so each thread receives a chunk of the array, and then sorts its chunk. Then, in step 3, the threads distribute the data. We partition the array again, but using a different strategy. Threads receive cells that are spaced by an offset. Then they distribute the data in the cells that they are in charge of. The figures on the bottom show what happens. So even though the array is not really sorted, you see, we still have like unsorted data. It's much closer of being sorted now. And then we will have less divergences. And with these optimizations, we conclude our class on divergence analysis. Most of the developments in this class are described in the paper Divergence Analysis, which was published in TOPLAS in 2013.